green packet. We got 3 definitions we need to talk about today. Starting with the real numbers. The real numbers.
It's not a show on TV. You guys don't watch the real numbers? Okay, because it's made up. What are real numbers?
Real numbers.
That's a great question, Mr. Tokar. I was just thinking, what are real numbers?
The real numbers are all and any point that can be plotted on the number line. Okay? It encompasses both the rational and all of the irrational numbers. All the real numbers are all of the numbers we could plot on the number line. Okay? It can be repeating, it can be a decimal, it can be a fraction, it can be positive, it can be negative, it can be 0. Any number that you can plot on the number line, positive, negative, or 0, is a real number. It's all the numbers you've used all your life. Okay? It encompasses all numbers on the number line. Both real or rational and irrational. Okay? Any point, does not matter if it's a whole number, a positive number, a negative number, in between, a decimal, a fraction. Any point on the real number line is a real number. Okay? Because one day, not too far in the future, you will learn about the non-real numbers, imaginary numbers. But not this year. Yes.
They thought I was kidding, Mr. Tokar. I said imaginary numbers, and they're like, that's not real.
Numbers that don't even exist, but we use in math. Without them, we can't do anything with electricity. It's used in electronics, transistors. Okay, so now let's break it down. We got the real numbers. We'll go over how to do those. Okay, so within the real numbers, okay, so imagine the real number is like our box that holds other types of subcategories, other types of number. So inside our real number box, we have rational numbers and we have irrational numbers. Okay, you've heard these words before. A rational number is a number that can be written. It's a number that can be written. A number that can be written without a never-ending
story.
Great movies.
You were going there.
Never-ending decimal. Okay, a number that can be written without a never-ending decimal. So it can be written as a fraction, again, positive, negative, doesn't matter, 0, as long as it does not have a never-ending, non-repeating, non-terminating decimal. So, for example, I always like to write a couple examples. Okay? 3 is rational. 0 is rational. -2 is rational. Even fractions are fine. 1/4, that's fine. Decimals, 3.265, that's fine. As long as it is it non-terminating? Okay? As long as it's not non-terminating.
How do we write a number that is repeating?
Ah, yeah, let's write a repeating.
You've seen it. How do I look at what gives away a number that says this is repeating? A line where? Over the number that's what? Repeating.
Okay? Even 0.333, that's a repeating number, that's allowed, rational. Okay? These are our rational numbers.
Because we know what the next number after 3 is going to be, right?
Okay. Next we have irrational numbers.
Why's it got to be irrational?
Rational.
You gotta think of it.
An irrational number is a number that is non-repeating and non-terminating. Non-terminating, meaning it has no end. A number that is non-repeating
Different numbers. We're not going to be able to predict what's next.
and non-terminating.
I'm going to get crazy here, guys. What, in terms of like just letters, what 2 letters prefix are on that make it rational, irrational? IR, right? Can you guys think of any other words with IR that mean not? If you're not responsible, you're irresponsible. IR means not rational, not responsible. They just learned about the prefix. Ear.
Okay, let's write one. Pi.
Love it.
3.1415925. And it keeps going on and on and on and on and on and on. Can't predict. Keeps going and going and going and going. Nothing repeats. It's just a decimal that changes and keeps going on and on and on and on. One day in the future, in Algebra 2, you'll learn about the exponential constant e. It's just like pi. 2.71, blah, 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 blah. Keeps going and going and going and going. Can't predict.
Infinity.
Another one that shows up a lot is when there's radicals. Remember we talked about those check marks, the square roots, third roots. A lot of time irrational numbers come up there too, like the square root of 2. We write it like this because we can't actually write down the exact decimal for the square root of 2. If you put that in your calculator, you just get a number that goes on and on and on and on and on and on and on. It can't be predicted. It's just random numbers that go on and on forever. Okay, so that's irrational. If you can't write down the exact number, then it's irrational.
So guys, can someone give me an example of a radical that isn't irrational?
Square root of...
What's the number that we can square root and get a nice whole number?
Yeah,
Perfect.
square root of 9. That's rational because we can write it as 3. We can write the entire number. Square root of 2, you can put that in your calculator. You cannot write the whole thing down. Your calculator can't even show you the whole number because it goes on forever. Forever and ever.
Because there's no number times itself that gives me a nice whole number, right?
Okay, another good note you can make off to the side, I'll do it in purple, is rational numbers. These can be written as fractions. Irrational numbers can't be written as a fraction. Irrational numbers, usually the dead giveaway is we need some type of math symbol to write them, right? Pi. We don't write 3.14 because we can't write the entire thing. So we use a symbol. E, which we won't use this year, but needs a symbol to represent the infinite number. Square root of 2, we don't write down what the square root of 2 actually is. We write the square root of 2 using that symbol because we can't write our exact answer otherwise. Does that make sense?
You hear your whole high school career writing the number out. We don't want it.
Okay. This year we'll dip into both areas. We'll be all in the real numbers this year. We won't go into imaginary, but we'll talk about rationals, we'll talk about irrationals. There's a lot we'll do this whole year. Okay. Okay. You do not have to write this whole thing down. But what I want to do with you is I'm going to pull up Desmos and put in some of these irrational numbers so that you can see what it looks like to determine if something is rational or irrational. So this is kind of like what it looks like. Like our real numbers is our big box. Okay? Inside the real numbers, we have our rational numbers, which are like our integers, our whole numbers. And we have our irrational numbers off to the side, our numbers that are non-terminating and non-repeating. So I'm going to pull up Desmos and just show you what you could do to help determine if a number is rational or irrational. Okay? Oh yeah, it's in one of the drawers. There's a big stack of them. So for example, if we look at some of our rational numbers, okay? If I want to see if 2/3 is rational, I can type it into Desmos. So if I type in 2/3, I can see that this is rational. But why is there a 7 at the end? Because Desmos doesn't give us the little repeating line. So what does it do at the very end? It what? It rounds it up. So when you see something like 0.6 repeating, and a 7 at the end, that's Desmos' way of saying, hey, this repeats. Okay? So a repeating decimal is rational. And we can try another one. -8 over 17. Okay? Here we go. Does that look irrational? Kinda, yeah. But this is rational. If it were irrational, Desmos would show some dots at the end. Also, if it can be written as a fraction, that means this decimal has an end. Okay? Even though this is a really long gross decimal, if it can be written as a fraction, it's rational automatically. Okay? Irrational numbers can't be written as a fraction. Okay? If we go ahead and look at our irrational numbers, I just got to switch to the other side. Whoop. And type these in. If I type in pi, you can see decimal that goes on forever and ever and ever. If I type in the negative square root of 10, 10 goes on and on and on and on and on. Can't be written as a fraction. If I type in the third root of 2, third root of 2. Again, we have a number that goes on and 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 on. Random. Can't be predicted. Okay, so Desmos, or your calculator, is a tool that you can use to help verify if something is rational or irrational. Okay? Next. Write down these examples. Example 1. Example 2. Example 1. Determine if the following numbers are rational or irrational. When you're writing these long examples down, you do not have to write them word for word. For example, I could rephrase example 1 is, I could just write rational or irrational question mark, right? That means the same thing. So these are how they would ask the questions on like a standardized test, like an OST. They're really wordy, long. and sometimes the directions get confusing. So it's good practice when you are writing notes to summarize our question. Example 1. Rational or irrational? Explain. That's what this question means. Even though it's like, determine if the following numbers are rational or irrational. Then justify, right? That's wordy. Tests like to be wordy. Wordy. You're done writing down example 1. You can start to think about A, B, and C. Is it rational or irrational? And then justify why. Put it away. Act classic. You need to be here. Get in your notes. Okay. A. Negative 2.45. Rational or irrational? Rational or irrational? Huh?
Don't be afraid, guys.
Rational or irrational?
You can either be right or wrong.
Remember, the check is, does the decimal go on forever? Does negative 2.45, is that decimal going on forever and ever and ever? No.
No repeating line.
Okay? And it's non-repeating. Okay? I mean, this is fine. You can write this down as an answer. So this is rational. This is a rational answer. I'm sure you could also write negative 2.45 as a fraction. Negative 245 over, over 1,000. Or whatever. You can turn it into a fraction. Okay, B. Rational or irrational? Irrational, because pi does what? It's a repeating, non-repeating, non-terminating number. It's random and goes on forever. We can't write it down exactly without the symbol. Irrational. Right? Those keywords are it's non-repeating and non-terminating. C, 5/7. Rational or irrational? Because it looks really gross on the calculator, but really, if you can write it as a fraction, then it's rational. But that's why these are tricky, because when you type in 5/7 into the calculator, it's not a nice number, right? It looks like a long random decimal, but if it can be written as a fraction, it's automatically rational. Pi can't be written as a fraction. We had to make a whole new symbol. So, rational. Fractions are always rational. Always, always. But they can try to deceive you because you type in fractions and sometimes they look like they're repeating and nasty. This is not repeating because it can be written as a fraction. Okay, example 2. Write it down. Use the definitions of rational and irrational to justify each statement. True or false? Okay, we can always summarize this instead of having to write that whole problem out is true or false? Explain. Is Is a statement true or false? Then explain. That's what justify means, explain. Okay, where? Look at your guys' beautiful notes. Use the definitions of rational and irrational numbers to justify each statement. Are your hands getting tired? My finger always starts to hurt. I squeeze my pencil so hard. Really bad habit of it.
Pushing things on.
I need to, but like I have like
Yeah, I know you're
a bump right here because I just squeeze my pencil so hard. I don't push down hard. I just hold it so tight. Too strong. Okay, A. You might be still writing, but let's look at A. The square root of 5 is an irrational number. Is that a true or a false statement? Brian says true. Who thinks true? I think true as well. If you take your calculator out and type in the square root of 5, okay, you get 2 point something, and it goes on and on and on forever. And if you were to try and tell your calculator to turn it into a fraction, it can't do it. This is a true statement. True. And what would be our justification? Why is it true? We can look at our calculator and see we have a gross decimal, but why is that true? Why is it irrational? You had to say. Yep. So it's non-repeating and it's non-terminating, which means it's random numbers forever. Okay? B, -5 is a rational number. True or false? True or false? Does this have decimals that go on forever, non-repeating? Or repeating? Non-repeating? No. Does it have a non-terminating decimal? Nope. This is true. This is rational. B is on here because a lot of times students think that negative numbers are what? A lot of students like build up this idea that, oh, negative numbers, that's not a good number, it's irrational. Negative doesn't mean anything. Doesn't mean it's irrational. Okay? C, tricky. 5.26262626 ... is rational. True or false? True. If I were to draw my little bar, where would it go? Above the last 2 6. Because what's repeating? 2 6, 2 6, 2 6. Since this is repeating, it's rational. Irrational numbers are non-repeating. So this is true. True. Okay. True. Alright, we have one little topic, one more example. This is going to be the new part, right? Did you guys pretty much know all that?
No.
Or at least you've heard the terms, right? So here's like how Algebra 1 works. We start off with something familiar, right? We're familiar with the real numbers. You have at some time heard the word rational and irrational, but this is the Algebra 1 new thing. It is called closure. Okay, this is the last little definition and thing we need to know. What is mathematical closure? What does it mean to be closed? Okay, closed or closure. A number has closure if the result of the operation is in the same set. Get that written down and we'll talk about what that nonsense means. Closure. Don't worry about the red yet. Just write the black up top. Closed or closure? Both meaning the same thing. A number has closure if the result of the operation is in the same set. This is what this wordy nonsense means. Let's look at this first problem. You're asking yourself this question, okay? What this means is you're asking yourself, where did I start? And then you're saying, where did I end? Okay, this is what closure is. Where did I start? Where do I end? If we look at the first example, we started with the number 5, right? This is where we started in our math problem. Is 5 rational or irrational? 5 is... What is it? 5 is a rational number, right? It is in the set, that's its set, it's in the set of rational numbers. We start with rational. Now we're going to look at, okay, where did I end up? I started in the rational number set, and where am I ending? Am I ending in the rational set? Right? Is 4.5 rational? Yeah, it is. 4.5 is rational. So I started as a rational, and I ended as a rational. So that means this problem has closure. We start and end in the same rational numbers. This has closure. So we would say this problem is closed. If I look at my my second problem, again, I'm starting with 5, which is rational. And after multiplying it by the square root of 3, I end up irrational. So I started rational, and I ended irrational. I'm just using IR because I'm lazy. So is this second problem closed? Not closed. It does not have closure. Not closed. Because we ended in a different set of numbers, we say that it is not closed. Okay? Not closed. Okay. I want you to ignore that bottom. I don't like it. Okay, can I go next? You don't need to write down the red. I hate the red. I don't like the way it's worded. Good? Okay, one last example. Example 3. To prove that a statement is false, you only need to find one counterexample. Okay? Determine whether each statement is true or false. If false, give a counterexample. So, we're going to read the statement. We're going to say, is it true or is it false? write example 3, true or false. Okay? The thing is, if it's false, we have to provide an example of why it's false. Okay? If we provide one example that proves the statement wrong, then that means you've proved it false. I'm going to make this bigger for you. That's better. Okay, these are hard. I would say these are hard because we have to create an example to show it's true, to show it's false if we think it's false. So E is saying irrational numbers, okay, non-terminating, non-repeating, are closed under addition. What that means is if I take an irrational number, no matter what I add to it, it will always stay an irrational number. So give me an example of an irrational number. Can be anything. Right? It's a number that goes on and on forever. But for simplicity, what's an easy irrational number? And we use a symbol that's easy to write down. Pi. Pi is irrational. So this is asking us, is there anything we can add, because it's closed under addition, is there anything we can add to pi so that it's not an irrational number anymore? For example, if I were to add 1 to pi, would it still be irrational? Yeah. Is there anything I can add to pi to make it not an irrational number? No. There is exactly one thing I can add to pi to make it rational. If I add negative pi to pi, what do I end up with?
So you've added 2 opposite numbers.
Now it equals 0. And is 0 irrational? Yeah. 0 is rational, right? So, are the irrational numbers closed under addition? No. This is false. A false statement. Because if I take pi and add negative pi to it, it's not irrational anymore. So it's not closed. This is my counterexample to show that this is false. That's why these are hard. These are hard problems. Okay, let's look at the next one. The sum, what does sum mean? What operation? Adding. Yep. The sum of a rational and an irrational number is a rational number. So the best way to do these is let's just make an example, because they don't give us numbers. It's kind of up to us to use our imagination. So, the sum of a rational, what rational number do you want to use? Doesn't matter. Any rational number. 4, 2, sure, we'll do 4. Okay, so my rational number is 4. And it's the sum, so I need to add an irrational number. What irrational number do we want to use? Sure, let's stick with pi. Let's add pi. What is 4 plus pi? Well, pi is 3.14, and if I add 4 to it, it'll be 7 point,
So the whole number changed, but it's still going on forever, right?
So this statement was saying the sum of a rational and an irrational number is a rational. Is that true? Look, we added a rational and an irrational, and what did we get?
Still keep going.
It's irrational, so this is not a true statement. This is false. And that's our counterexample, 4 plus pi. Good Lord, what happened? Okay. Irrational numbers are closed under division. We're running low on time, so I'm going to speed you through. Irrational numbers are closed under division. Just to keep things simple, let's say I have pi again. What can I divide pi by to make it not irrational? There's only one thing.
Think about division, guys. What's the only thing that you can divide by that will cancel it out?
I hear 1, and that's the on the right. Pi divided by what gives me 1? Goodness. Pi divided by what gives you 1?
What's the rule for division? What?
Pi.
Yeah, any number divided by itself.
Pi divided by pi is 1. G is trying to tell me that no matter what I divide pi by, it's going to always be irrational. But that's not true. If I divide pi by pi, I end up with a rational number, 1. So this is false. False. Last one. The sum of a rational and irrational number is a real number. This is tricky vocab. I'm not even going to write anything because real numbers are which numbers? In our definition, what's a real number? Can a real number be a rational number? Can a real number be an irrational number? So this statement is saying the sum of a rational and irrational is real. Isn't that true? Yeah. The real numbers are all of the numbers. So it doesn't matter if I add or subtract or multiply or divide any combination of real and rational. We're always going to end up with a real number. So this actually is true. True. Why did you put the opposite? That's what? They don't do that. No, you have to submit. You can go to Perry's office after this class, and then you have to write a statement, and then they decide. You can't just walk in and ask to look at the cameras.
Because
They can't show you the camera because it has.
But you have
But
to
you
ask
have,
him
you have to
to
have
provide
Perry write you a statement and give you a reason to look at the camera. You can't just ask them to look at it for you. So you can go to Perry and ask to write a statement.
Right now.
After the period, you can run to our office right here around the corner. What? She'll write you a pass, and administrators give you an excused pass to any class. Put your things away, slide it into the face. Your quizzes are in there, and I believe your grades are all up to date. I have your everything set, good to go. Have a good one. Sorry I talked your ears off today.